As we know that the product of vectors is one of the properties of vector, and we have seen that the multiplication of vectors by a scalar product was only a number or a scalar quantity. The goal of this session is to start the definition of another type of multiplication of vectors, that is the cross product. Well, the cross product of two vectors A and B is defined only in three-dimensional space, and it is called a cross due to the cross sign separating the two vectors in the multiplication process. Now, the result of this cross product is actually a third vector, maybe called C. This vector C is perpendicular to the plane of both vectors A and B, and its direction is given by the right-hand rule, and this will be demonstrated later on. However, the vectors A and B form kind of parallelogram in the plane, and the magnitude resulted in the vector product AB sine theta actually equal to the area of the parallelogram that the vectors span. To find the direction of the cross product, that is the direction of C, we're going to use the right-hand rule. And this rule, the sequence of multiplication of the two vectors is important. As long as we are starting with the vector A and then going in this way in the counterclockwise direction towards vector B as shown in the diagram, in such case, we're going to use the right-hand rule where the four fingers of your right hand is going to be rotating in the direction of counterclockwise, making a circle, where the thumb is going to be perpendicular to this circle upward, and this represents the direction of the vector C. Alternatively, you can think of it in this way. If you want to tighten a screw into the ceiling, so what you do actually, you go by using the screwdriver in this way, where the four fingers is going to be in this direction. However, the direction of the screw will be upward like this. Some other people might use the right-hand rule differently. They use the three fingers that are the index finger, the middle finger, and the thumb. When they put the index finger along vector A and the middle finger along the vector B, in such case, the thumb finger, which is perpendicular to them, will be along the vector C, and this will be demonstrated later on in an animation. How about if we change the sequence of the two vectors? Instead of having the product A cross B, we're going to have B cross A. The direction of the new vector D, using the right-hand rule, obviously is different from the previous one, where we are going to go now from B in the clockwise direction towards A. In this case, the rotating circle of your fingers is going to be this way, where the perpendicular to these rotating fingers to the circle is going to be downward, and such that the vector D is downward. Using the screwdriver, now we're going to tighten the screw into the ground instead of the ceiling, where the direction of the screwdriver will be clockwise direction, and screw will be going into the ground instead. Obviously, the cross product depends on the sequence, so A cross B is not equal to B cross A. However, their magnitudes are the same, but they have different directions. In the dot product of the two vectors A and B, we used to have the result AB cosine theta. So we were interested in finding the projection of the vector A along the direction of B because we got a result with cosine theta. In this product, the result is AB sine theta. So how can we get sine theta in such diagram? Actually, sine theta is related to the component of B perpendicular to the vector A. That is B sine theta. So what about if we have alternatively this diagram? So in this case, we are interested in finding the component of the vector A perpendicular to the direction of the vector B, and then we'll have A sine theta. Well, the magnitude of the two vectors A and B then can be defined as the magnitude of the vector A multiplied by the component of vector B perpendicular to A. Alternatively, this can also be understood as the magnitude of the vector B multiplied by the component of the vector A perpendicular to B. In both cases, the magnitude AB sine theta actually equals the area of parallelogram that the two vectors A and B span. And this obviously depends on the value, the magnitude of A and B and the angle between them. What we can conclude from our previous demonstration for the vector product is that the sequence of multiplying the two vectors A and B is really very important. So the student has to be very careful when multiplying the two vectors and should understand that the product A and cross B is different from the vector or the cross product B cross A because the direction of the resulting vector is different. Also, the magnitude of the vector product is found to depend not only on the magnitudes of the two vectors, but also on the angle between them. Next, we're going to show an animation that demonstrates the importance of the change in the angle between the two vectors on the final result.
We'll use these animated vector arrows to show how the cross product of two vectors varies as the angle between them is changed. The cross product of these two vectors, A and B, is a vector at right angles to both. Its direction can be found using the right-hand rule. The magnitude of a cross product of two vectors is equal to the product of their magnitudes times the sine of the angle between them. Here's how the cross product of A and B changes as the angle between them is changed.
When any two vectors are given in terms of their unit vector notations, I hat, j hat, and k hat, like A and B here, how can we carry out the cross product using these notations? Well, we can't carry out the cross product unless we know how these unit vectors, I hat, j hat, and k hat, behave in their cross product? Well, to do that first, we have to use the cross product relation A cross B equals AB sine theta multiplied by n hat, where n hat refers to the direction unit vector, refers to the direction perpendicular to the vectors A and B. Applying this to the similar unit vectors like I hat, for instance, I hat cross I hat in this case is going to be 0 because the angle between the two parallel vectors I hat and itself is 0, and this goes similarly for j hat cross j hat and k hat cross k hat. Well, for different unit vectors, let's start with I hat and j hat. The cross product of I hat cross j hat is going to be equal to k hat. That is because the magnitude of the vector I hat is 1, and the magnitude of vector j hat is 1 as well, and the angle between the two vectors is 90, and sine 90 equals 1. So the magnitude of the cross product is equal to 1, while the direction is going to be found by applying the right-hand rule. That is, I hat cross j hat is going to give us a perpendicular unit vector k hat. Similarly, for the two vectors j hat and k hat, the cross product of them is going to give us a magnitude of 1, and the direction, we're going to apply the right-hand rule, and the direction is going to be the vector unit vector perpendicular to both of them. That is I hat. However, if we decided to reverse the sequence by using the cross product k hat cross j hat, and the answer is going to be minus I hat instead. Finally, for the cross product of k hat and I hat, this cross product is going to give us j hat, where the right-hand rule indicates that the perpendicular vector to both of them is j hat. However, if we reverse the sequence, we're going to get an answer of minus j hat for the cross product of I hat cross j hat. Now we can proceed in conducting the cross product of the two given vectors in terms of their unit vector notations as follows. Writing down the vector A in terms of the component vectors, the three component vectors, and the vector B, which has also three component vectors, and we'll carry out the cross product of these three component vectors in the parentheses together with that of the other one in the other parentheses. The first component vector, start with the first component vector A with the first component vector of B, and then again first component of vector A cross together with that of component vector of B, and then finally again the first one with the third component vector of vector B. This gives us the result as follows, and then we'll start multiplying the second component vector of A by cross product with the first component vector of B, and then also the second component vector of A with the second component vector of B, and then again the second component vector of A with the third component vector of B. This will give us this result. And finally, we're going to go for the cross product of the third component vector of A with the three component vectors of B, starting with the first one, and then again with the second one, and then finally with the third one. And this turns out to be like that. So we have nine terms containing cross product of unit vectors of similar unit vectors and different unit vectors. Regarding the cross product of similar unit vectors, these will give us a 0 answer. For the different ones, starting from first I cross j hat will give us k hat, and j hat cross k hat equals I hat, and then k hat cross I hat equals j hat. For the other ones, I hat to cross k hat will give us minus j hat, and j hat cross I hat will give us minus k hat, and then finally k hat cross j hat equals minus I hat. What does this result give us? Well, this result gives us terms for I hat and j hat and k hat. For I hat with 2 terms, and for j hat another 2 terms, and then finally for k hat with 2 terms. Now, collecting the coefficients of I hat altogether will give us ay bz minus az by, and then that for the j hat az bx minus ax bz, and finally for the k hat ax by minus ay bx, while the final answer is a vector quantity represented in terms of I hat, j hat, and k hat. Calling the cross product equals C, this means we have 3 components for C: Cx, which is equal to the coefficient of I hat, and Cy, which is equal to the coefficient of j hat, and then Z component, which is the coefficient of k hat.